Welcome back to this course on causality for social science, causal inference, directed acyclic graphs, and machine learning. This is part one, the motivation. And I wanted to preface this section just by quoting Termulin and Ashcroft, who said that to question the foundations of a discipline or a practice is not necessarily to deny its value, but rather to stimulate a judicious and balanced appraisal of its merits. So in order to motivate causality, I think it's interesting to see where we are today and to critique where we are today. And in doing so, obviously, there's a chance that I sort of step on some toes. But I want to sort of reassure you that this comes from a place that it's motivated by the desire to improve practice, not to sort of tear it all down. So I hope that sentiment is evident. So why do we need causality? I'm going to start with these two quotes here. One by Van Dongen, who said that well-developed scientific theories facilitate the classic scientific goals of understanding, prediction, and control. And the second quote, which may seem slightly unrelated, is by Judea Pearl, who said there is nothing in the joint distribution of symptoms and diseases that tells us that curing the former would or will not cure the latter. And I want to convince you, actually, these are both telling us that causality is important. So the first quote, it says that these theories that we have in social science and psychology need to enable us to do things like understand phenomena. They need to help us control phenomena, that is, to manipulate our environment in order to achieve a desired effect without nasty surprises. And similarly, prediction is actually arguably an easier task. It's sort of subsumed within the goals of understanding and control. The idea being, as we understand something, we can also predict what will happen. And similarly, Judea Pearl here is talking about causality as well, because he's arguing that, well, just because we know about symptoms and diseases, it doesn't tell us whether or not what the causal relationship is between those two things. And so we can have all the data in the world, but we won't be able to answer fundamentally fundamental questions. And some examples about this, which are taken from the literature. Going to hospital is correlated with being sick. So if you look at the rates of sickness and also the rates of going to hospital, you'll see that they're strongly correlated. And usually when we do our research, we identify these strong correlations. We make recommendations. For instance, we might identify that going to the hospital is a risk factor, and therefore maybe we should stop people from going to the hospital to reduce the number of sick people. Notwithstanding the fact that sometimes people go to hospital and do contract new diseases, actually we understand, this is an obvious and trivial example, that actually people are going to the hospital because they were already sick and they're going there to get better. So even though this is a trivial example, obviously our own research is not trivial. That's why we're doing work on it, I assume. And therefore, when we're presented with these correlations, we have to be able to draw some kind of meaningful conclusion, not one that is the opposite potentially of what we should conclude. Another example, which is actually taken from Brady Neal's course, going to bed with shoes on is correlated with waking up with a headache. The idea is, if you look at the co-occurrences of waking up with a headache and whether or not they went to bed with their shoes on the night before, you see that they do indeed co-occur. And again, we might then suggest that people should be prevented from wearing shoes to bed in order to reduce headaches in the morning. There's actually a third variable at play here, which is alcohol consumption. The idea being that if people consume alcohol the night before, they're more likely to go to bed with their shoes on and also, of course, wake up with a hangover. And so causality is really essential when understanding the world beyond these two trivial examples, so that we can actually manipulate, improve, modify, and intervene. We don't want to stop people from going to the hospital. We may encourage people to not go to bed with their shoes on, but not for the reasons associated with headaches. So we want to be able to manipulate and intervene in our environment, in our real world, not get nasty surprises, to do so in an intelligent way. And in order to do this, we need causal knowledge. And this enables us to move beyond very predictive questions, such as when is something going to happen, which thing is going to happen, or how much of something is going to happen, and instead move towards answering questions like how something happens, why it happens, and what if we were to do something different, what would happen, in a sort of counterfactual way. And non-causal methods don't respect these distinctions between sort of prediction and causation. So we really need to move beyond these things. Now, it's reassuring that in psychology and actually in most of science, our theories are somewhat causal. They're motivated by causal observations. They describe processes that occur in the real world. And it's just as well that they do that, because otherwise it would be very difficult to know what to do with that information. But to that extent, I don't have to convince you too hard that you need to consider causality for your theories, because I see a lot of causality in theories already in psychology. So for instance, if I say something aggressive, you're likely to respond to that in a certain way, and so on. And then we have these theories that describe these sort of evolutions of cause and effect over time. And so what do I mean by a cause? Well, still at a very philosophical level, I'm going to use Lewis's definition here, who said that we think of a cause as something that makes a difference, and the difference it makes must be a difference from what would have happened without it, had it been absent. Its effects, some of them at least, and usually all, would have been absent as well. And this maybe sounds a little bit abstract to the extent that it's kind of alluding to something that would have happened without something. And so if I take the drug, there's only one of me that took the drug, but I would like to somehow reason about what would have happened to me had I not taken the drug. And this goal, it sort of alludes to sort of parallel universes in the sense that we only have access to one reality, but we want to draw inference about another potential reality that may not have actually come to occur. And whilst this sounds almost a bit sci-fi, actually this is the goal of, for instance, randomized control trials, to assess on average what the effect of a drug is to reason also about what would happen if people didn't take that drug. So even though it sounds quite philosophical, it's actually quite a tangible quantity. We obviously hear this a lot in terms of where we are today. Correlation is not causation. And I think this is a mantra that is generally given quite commonly and frequently today in statistics classes. Everyone's always said this. I would like to start sort of putting in this not necessarily causation here, to at least acknowledge the fact that we have over 100 years of research in the domain of causality that can actually help us move from correlation to causation. So to say that it's not causation is almost to deny the possibility, where actually, no, it certainly is possible. And that's what I want to sort of, I guess, cover in this course. Now, why is causality not already taught frequently as part of undergraduate courses in statistics? I would love that to be the case, but actually there's a very strange history behind it. Indeed, Dowd has described the literature on causal inference as one of the oddest literatures in all of academia. Refers to certain quotes about the past 100 years being labeled a century of denial, Bertrand Russell called stupid, and where pillars of the field are oblivious to decades-old developments. He says, how is it the most important question in all of empirical analysis could remain so controversial after being considered for so long a time by so many brilliant minds? And I would actually recommend the interview with Judea Pearl that recently came out, that was referenced in the resources section of the previous video, just to have get a feel for sort of what's been happening in that space regarding the history of causality. And it is a very strange, very interesting history. I'm not going to talk about it. I'm just going to acknowledge the fact that actually there is this bizarre history behind causality, and it can sort of explain a little bit as to why it's not being taught as much as it is today. Indeed, there are other papers as well that allude to this problem, the sort of perspective of causality. Miguel Hernan refers to causality as the C word, and encourages us to actually take it seriously, to move beyond these scientific euphemisms and to be sort of honest with ourselves about what we want to achieve, which is by and large the estimation of causal quantities. So he says here, scientific euphemisms do not improve causal inference from observational data, and he argues that that's still a fundamental and foundational task as scientists that we wish to undertake, but we can't because we're sort of stopped by the weight of primarily tradition. He describes this process of how you might get a response from the editor who says, dear author, your observational study cannot prove causation. Please replace all references to causal effects by references to associations. As a result, causal effects in terms with similar meaning are routinely avoided in scientific publications that describe non-randomized studies. Instead, we see terms like association or others that convey a similar meaning, like correlation, pattern, or the calculatedly ambiguous link. Miguel goes on to say we need to stop treating causality as a dirty word that respectable investigators do not say in public or put in print. And whilst it is true that observational studies cannot definitively prove causation, the statement misses the point. So it's a highly recommended paper to get some context around how people deal with causality today in scientific publishing. There's another paper that has a similar sentiment by this group of researchers here called The Taboo Against Explicit Causal Inference in Non-Experimental Psychology. And they allude to this sort of mantra, correlation does not imply causation. Of course, this is true, but it's a bit of a truism to the extent that it's kind of obvious and doesn't help us engage seriously with the alternatives. and really we should move beyond this. And they describe this, how this taboo has resulted in a dilemma. On the one hand, causal relationships are of central interest. On the other hand, they are forbidden when experiments are unfeasible or unethical. As a result, one might expect non-experimental researchers to limit themselves to descriptive or predictive research questions, but they don't actually avoid asking causal research questions. They just sort of do so in an implicit and opaque way without clear articulation of the underlying assumptions. So given that fundamentally what we care about is causation, just because we don't have experimental data doesn't mean that we should somehow guise our research or disguise our research as observational and associational, even when actually what we're fundamentally interested in is a causal quantity. So as a summary then, in terms of causality, and where it is in the empirical domains, we see that it's been neglected. The tools are there. We've got 100 years of research, and I'm going to talk about some of those tools on this course. Causality is central to science. We kind of do it anyway, but we do it in an opaque way that's not transparent, kind of trying to sneak causality in there, but acknowledging that maybe it's not possible. And so we don't really seriously engage with those techniques. And so actually the resulting quantity shouldn't really be called causal at the end of the day, even though it's fundamentally what we want. It's just done so in a non-rigorous way because, well, why do it seriously if we're going to get told we can't do it anyway? And so this leads to actually a lot of meaningless inference. A lot of the quantities that we end up with can be highly biased, and they correspond neither with associations, really. They're sort of very particular and bizarre quantities, but they are also not really causal quantities because they haven't really been derived properly. In terms of our theory, this was one of the three other main points of this course, is to help psychologists develop their theories, and to start off with a very blunt and damning quote by Anne Scheel, who said that most claims in this is the psychology literature, are so critically underspecified that attempts to empirically evaluate them are doomed to failure. They are not even wrong. Meta-scientists should beware of the flawed assumption that the psychological literature is a collection of well-defined claims. And to move beyond the crisis, psychologists must reconsider and rebuild the conceptual basis of their hypotheses before trying to test them. And this work sort of alludes to the fact that in psychology, we don't really have a formal framework or process. We don't teach a process for how to develop and specify theories. There are groups of researchers working on this, of course. But it's nonetheless one of these sort of things that just sort of happens, and there isn't any clear way to do it with recommended steps. And by consequence, we end up with a lot of theories that are very verbal, that are non-mathematical, that are very flexible, that can sort of be adapted to any new result. And I think we often end up getting a result, and it's sort of feasible to fit that result to just about any theory that we want to, because those theories are flexible enough to sort of admit these different results. And as a consequence of this flexibility and vagueness, these theories are also very untestable, because it's not clear how our hypothesis relates to a particular aspect of the theory. It's not clear how our statistical model relates either to the hypothesis or to the theory. And so what we end up with is actually a very loose and circular process that doesn't really move in a positive direction. And there was this article on Medium by Nettle, which was, I think, captured this very well. He said that a problem with much of psychology is that we had to pretend to have theories even when we're just describing phenomena or proto-theorizing. And so I'm going to use this term a few times throughout, this proto-theory, proto-theorizing. And they go on to say this is why our discipline is full of silly sounding theories like five-factor theory, which is the theory that there are often 5 factors, or social identity theory, which is the theory that people have social identities that are important, or statements like life history theory predicts, where the actual empirical regularity seems to bear no relation to the cited body of formal theory. Another reform they would like to see is that people don't feel a need to claim they have a theory when they're actually just doing this proto-theorizing. At present, people are as guilty of citing, which is calling it theory for effect, as they are of harking, hypothesizing after the results are known. And they say that it ought to be quite fine to say that we are testing some intuitions about what kinds of factors affect the process or investigating different ways of measuring something, with the cheerful admission that there's no real theory yet. And actually, part of this motivation is not to discourage you and make you feel like, we've only got crap theories, or for you to think that that's what I'm trying to convey, but rather to be a little bit more realistic about the strength and formalism of our theories. And here is to say that, we don't need to be embarrassed about the fact that we might be at the early stages of research, and to have a proto-theory is absolutely fine. And it's just the first stage in a very long process, potentially, to really formalize that theory and test it properly. So in terms of the sort of cycle of how we are now, we might start with a theory that we call a theory today, but is maybe more of a proto-theory. And this theory is very vague, underspecified, and verbal. It's non-mathematical, it's non-formal. And we might use that to form a hypothesis. But as a consequence of the vagueness of the theory, the hypothesis is also often verbal or non-mathematical and can't be unambiguously tied to the theory. It's also very sort of flexible in that way. And to that extent, we can design a study to test this hypothesis. At that point, we have lots of other problems that I'm not sort of talking about as part of this course, things like measurement problems, missing variables, censoring, and so on. So all of that's a big sort of weak link in the chain, and it's a very important link to work on, but it's not something I'm addressing here. And then once we've got our data, we might be doing our analyses, but our analyses are only weakly tied to the hypothesis. There's not a direct link, certainly, with the theory either. And as a result, they're often misspecified, both in terms of their causal structure and in terms of the functions that we're using. So maybe we're just using a linear function when we should be using machine learning approaches. We get our results, but those results are kind of post hoc interpreted. They're not meaningfully informative because of the misspecification that occurred here. And then we somehow adapt them or assimilate those results into our theory, but it's not particularly clear how to use those results given the flexibility of the theory. And so where should our theories really go to? What should our theories have as properties? They should be able to explain the phenomena by representing the particular parts of the real world and the relationships among them that give rise to the phenomena of interest. And they should be relevant, precise, unambiguous, i.e. independent of the creator, falsifiable, generalizable, predictive, parsimonious. And there are many other lists of criteria. I see some other sort of researchers there for more information. And Sheil said, as part of this process, we need to be able to define concepts, measurement functions, which is the idea, when we capture the data, what is the function associated with the manipulation of, the state of the world into those numbers that we end up with in our data set. Causal structures is exactly what we're talking about as part of this course. The conditions and assumptions under which this theory is valid, under which it holds. And just to sort of zoom in on a couple of things. Firstly, this independence of creator. Of course, if we have a formal theory that's unambiguous, we can share it openly. People can look at it and they don't have to contact the initial creator of that theory to interpret it. It's very clear from the specification. It's not something that we need to contact the original creator to understand, how should I interpret this? Is it applicable to my problem? And so on and so on. It should be as formal and as independent of the creator as possible. And the other point here is parsimony. And I want to move on to the next slide just to talk about this. So I did have a background in engineering, and there we have some theories that I guess broadly look something like this. Here, the phenomenon is really this robotic arm, and we want to be able to control its movement. And so we end up sort of abstracting away from the individual particles and molecules that can comprise this robotic arm, and sort of lump them into various parameters such as joint angles. So we can measure the sort of angle between each of these joints, and then we can measure the velocity and the acceleration of those joints and try and control them. And this is actually the talk on a particular joint that describes the position of the end point here. And I wanted to show this because actually this isn't a very good model. This was actually done as a piece of coursework that I did. I could have done it a lot better. And actually it's a simplification, and it's already a big simplification, but it works still quite well. But this is the complexity of something as sort of basic as a robotic arm. And whenever we're developing our own theories, we have to decide on an appropriate level of abstraction from the phenomenon that we're interested in to sort of understand just where our theory should be in terms of complexity. And whilst I can't tell you where that is, I don't have an answer for how complex theories in psychology should be, I do have an intuition that perhaps they're already on the parsimonious side already. Some people may disagree with me. I'm very interested to engage in that debate. It's just when I look at this robotic arm and I see, okay, well, this is the complexity of our theory and it's mathematically formulated and so on. Maybe the equivalent sort of models and statistical models that we use in psychology and social science should sort of somehow reflect a little bit more the underlying complexity of human beings and human behavior, which I would argue is much more complex, at least on the face of it, than the behavior of a robotic arm. So when we're deciding on the level of abstraction and the assumptions that we're making, how parsimonious our model should be, we obviously don't want it to be too much, because we can move too much in either direction. We can try and make our model overly complicated and then it maybe becomes intractable. We can't estimate certain quantities and so on. But it may also be too simple, in which case our model will be meaningless. In terms of our general assumptions then, and this is going to motivate also machine learning, we assume that everything's sort of correlation, even when actually what we're interested in is causality. And that's kind of what we've talked about already. Also, our theories are assumed to be true by and large a priori, and they're not properly validated or tested. When we get an effect size estimate, the only thing that effect size estimate really tells us is the strength of the effect between two links in a causal process, or two nodes in a graph, as we'll come to see. But actually, that's not necessarily testing a theory. You could argue, well, if it's zero, then we can remove that link. But if it's non-zero, it just tells us the strength. So it doesn't actually help us test the theory itself. And to the extent that I've already said, if our theories are very vague, it's not also clear what that effect size really corresponds with as part of that original theory. So they're not arguably very testable anyway at the moment. We also assume that everything is linear, and that's a general sort of tendency in all of research in psychology to just use linear models. Van der Laan talks about these linear models, motivates the use of machine learning by describing these kinds of assumptions, the assumption that this linear model is linear and Gaussian and so on. These models that are so unrealistic that they are indexed by a finite dimensional parameter are still the status quo, even though everybody agrees they are known to be false. He also talks about the famous George Box quote, all models are wrong, some are useful. I think what we have to do is make sure our models are still useful. So even if we use machine learning, even if we use causality, we still acknowledge that we are abstracted from the reality, which is very, very complex. We're looking at we go to any level of arbitrary detail. But when we make these assumptions, we want them to not render the model useless. And I think it's very easy in psychology to sort of lose sight of what is a useful model and what is a useless model, because we don't really have ground truth. We're sort of doing statistical inference in the dark. And so it's very hard to know whether our models are too simple or too complex. But it's nonetheless something I want to raise, because when we when we develop our graphs, when we develop our theories, it's a key consideration as to how much complexity we want to include in that model. So motivating machine learning, then, this assumption of a linear model, if this curve here is the true model, then the true function rather, then this straight line here is a linear model. You can see this is a model with high bias. And what we might want to do is actually fit this nice smooth line here, which would represent the original function, which is optimal. We want it to be able to perform well on new data, and we don't want our function to have high variance to the extent that it's sort of fitting the noise rather than the underlying function. And so when we come to the machine learning stage, we want to learn how to do that optimally to get the most out of it, because obviously a risk with machine learning is that we do overfit our data, in which case we end up with just as bad results as if we had, say, a linear model in the face of a non-linear function. And that's motivated here. If we have the family of all models here, we kind of want to select the function which best represents our data. We have a whole load of functions, f1, f2, all the way to f infinity, for example. Whereas right now, what tends to happen is we select from a family of linear models here, where we're identifying the linear model with the best coefficients to explain our data. But nonetheless, the resulting prediction of the outcome has to be a weighted linear combination of the inputs, and that's quite a difficult task to do well. So with machine learning, we get these new concerns like this overfitting that I already mentioned, but also in terms of explainability, understanding what our model is doing. Is it fair? Is it leveraging spurious correlations or biases in the data that correspond with sensitive or culturally protected factors? We might get data leaks, so we might think we're doing really well, but actually we've just sort of found a shortcut in the data that makes us do really well without really doing well. And also statistical inference. So the second to last part of this course, we'll discuss how we can still do statistical inference with machine learning methods, that is, get confidence intervals and p-values. So in summary, our theories are often vague, verbal, causal, untestable. There's no formal process that we have to move from our sort of initial conceptualization of a phenomenon to a theory that's formal and unambiguous. As a result, we have arguably this theory crisis, which sort of exists in parallel with the replication crisis in psychology. And I would argue that there's also not enough triangulation. I'll mention that in just a second. But this obviously leads to replication issues as well. If we don't really know what we're testing, it's very hard to have two papers and argue whether or not they're looking at the same thing or not. We also have estimation problems due to these issues associated with functional misspecification, that is, using a linear model when it's actually nonlinear, and that can also contribute problems that are actually harder to detect than replication, because we might do the same thing twice. But if that thing is wrong, it doesn't help us understand whether we're moving in the right direction. It just helps us maybe feel more confident that our incorrect results are correct. The solutions to these problems are things like non-parametric models and machine learning, but also causality, formal theory specification. And we're kind of now ignoring all the difficulties associated with the measurement. Are we actually measuring what we care about? So that's a whole sort of other topic that's also very, very important. So all this is kind of worrying, and certainly as I was going through the sort of meta research for it, sort of doesn't fill you with any sense of optimism. But that said, we're at a really nice point in time. For one, I can share this course on YouTube, hoping that people will find value in it. And to that extent, we have access to all these open source code bases like GitHub, these repositories where we can, get good at something in a relatively short space of time. So actually, I think in my view, it's a good opportunity to start changing the way we approach research, because we have the tools out there that we can start to leverage to do things in a better way. I think the key thing is to maybe have our minds open to the possibility that the way we're doing science now isn't necessarily the best way to do science. And to acknowledge also that there are researchers that are concerned, like probably most of you are, studying something in the real world. And then there are also researchers who are concerned with studying how we research itself. So this sort of meta research angle. And so to say that, well, there's only one way of doing science, and that's the way we were taught at university, well, that's not quite true. That is also evolving in the same way that our understanding of the world is hopefully also evolving. So it's important to acknowledge that all of this is sort of a fluid process. So when I say triangulation a few slides back, what I meant is that we should really not be using one approach to develop our theories, but to acknowledge that there are multiple ways to sort of combine information from different sources. So for instance, when we first start to develop our proto-theory, when we're conceptualizing and talking about our phenomenon of interest, we may be using qualitative research to help guide us as to what things are important. That is, doing qualitative interviews with individuals to identify things that are important to certain experiences. And without that, we're sort of just guessing. We're saying, this concept is probably important to that. But that's really just based on your experience and your own anecdotes and inductive biases. So we should really be using, in my view, qualitative research to help us strengthen and bolster the proto-theory. And it might feel a lot like philosophy at this stage. If it does, that's not a problem. We can also use things like prediction, so machine learning, as I'll talk about later on, to really leverage, to identify important factors that are relevant to a particular outcome of interest, to start making sure, this proto-theory is consistent with the qualitative reports, and that it's consistent with the associations that we find in the data. And then at a certain stage, we need to start specifying our formal theory as a mathematical object. And to do that, these other things will obviously be useful. We also can do things like causal discovery, which we'll talk about, and causal inference. And then there's also another side of it, which I don't talk about, which is computational modeling. But there's a group at University of Amsterdam that are looking at this, and I do recommend it. In fact, we'll do a little bit of computational modeling as part of causal inference to make sure that the techniques that we're using work properly. And that involves simulating data to make sure our data look like what we expect, and to make sure our results look like what we expect. So I've got some notes here. I'll just step through these now. Theory can inform useful predictive variables. Theory informs data collection methodologies, and causal discovery helps us uncover unknown substructures. Simulated data can be used to check the validity of computational models. The main point here is that we're sort of going through a process of iterative triangulation. We don't just choose one approach and then call it a day, but actually we're going to keep coming back to this and updating things. This is an ongoing process. So in this course, then, I'm going to try and reframe some well-known statistical concepts like correlation in the context of what we actually care about, causality, and in a way which is theoretically consistent. So rather than there being a big gap between our theory and what we end up with, actually there's this sort of homogeneous flow between our causal theory, our causal proto-theory, our causal hypotheses, and our causal estimates at the end of the day. We want to deal with the causal inference part of this big theory analysis web primarily, but I'm also going to talk about causal discovery. And part of this process will force us to formalize our theory. So even if our theory is not quite ready for this, we're going to go through the process anyway to make sure we know how. And then with this formal theory, we can then specify our hypotheses as unambiguous functions or components of that theory. And then we can estimate the things that we really care about unambiguously. And we're going to try and do the estimation using machine learning, and to do so without making unreasonable assumptions about parametric form or functional forms. So in terms of the actual topics, I'll talk about directed acyclic graphs and a little bit about structural causal models, which provide us with the framework that we're going to use to formalize our theories. And I'll talk about control variables, what they actually are. I think for a lot of people, when they reconceptualize or reframe control variables from the perspective of directed acyclic graphs, they take on a very different meaning to what they had previously. As I said, estimation and machine learning, also some causal discovery. And after this course, you're going to start being able to formalize your theories, specify your research questions as unambiguous functions of your theory, be able to clearly state the assumptions underlying that hypothesis and the estimates, and then be able to use data adaptive techniques for estimation, thereby avoid unnecessary assumptions. This is actually a carryover from a course that I gave, so we're not going to go at your pace, we're going to go at my pace. This is a YouTube video. But I want to leave you with a set of exercises. So if you're following this course, I want to encourage you to start making sure you're doing this proto-theorizing well, and start thinking about the phenomenon that you're interested in, how you define that phenomenon, and what the relevant constructs and variables are. And the idea is that, as you go through this course, you can start to develop that further, add things on, remove links, add variables, and so on. And as part of this, ask yourself, are you interested in causal correlational analyses? Are you purely interested in a table which tells you the co-occurrence of events, or are you fundamentally interested in your theory, and is that theory causal? What language do you use when you're reporting and interpreting your results? And on the note of interpretations, for your own research at the moment, what language do you use when you're interpreting your coefficients from your linear models, for instance? Do you answer questions like how, why, and what if questions, or are you more asking questions like when, how much, and what type questions, which are more like associations? So that's it for this lecture, and I'll see you in the next one for some directed acyclic graphs.